So now let's consider the relationship between the line and phase voltages and current as well as the power, considering the two modes of connection that we have in a three-phase system. So let's start off with the star configuration. So under this, we are going to consider a balanced star-star system. That is a three-phase system in which we have a balanced star-connected source and also a balanced star-connected load. So we have three windings connected at a common point. That is called the neutral point. And then we have the loads connected at the terminals A, B, C. And the three windings induces voltages per phase. So we have VAN, VBN, and then VCN. So VAN is equal to V polar 0, VBN is V polar negative 120, and then VCN is equal to V polar plus 120 degrees. Now you realize that the phase voltages VAN, VBN, and then VCN have the same magnitude of voltage, except that they are out of phase with each other by 120 degrees. So the phase voltage is the voltage measured from any line to the neutral, and the line-to-line voltage, or better still, the line voltage, is the voltage measured between two lines. So we have the phase voltage Vp to be equal to the magnitude of VAN, and that is equal to magnitude of VBN, and then magnitude of VCN. So let's try to find the line voltage VAB. So the line voltage VAB is equal to, now we are going to take the positive sequence, that is the clockwise direction. So we are going to have VAN plus VNB, and that is the same as VAN plus negative VBN. Now let's substitute the values of VAN and then VBN. So for VAN we have V polar 0, and then VBN we have V polar negative 120. Now let's resolve these phases from the polar form into the rectangular form. So that's going to be V cos 0 plus JV sine 0 minus, we have V cos negative 120 plus JV sine negative 120. Now let's simplify. So V cos 0 becomes V, and then JV sine 0 becomes 0 minus V cos negative 120 is negative 1 over 2 V, and then V sine negative 120 becomes negative V root 3 over 2. Now let's simplify like terms. So we have V minus negative 1 over 2 V, that becomes 3 over 2 V, and then 0 minus negative V root 3 over 2 becomes positive V root 3 over 2. Now let's factor out V, so that inside of the bracket we have 3 over 2 plus j root 3 over 2. Now converting this back to the polar form, that becomes root 3 20 polar 30 degrees. Therefore, we say that VAB is equal to root 3 times 20 polar 30 degrees. Now, what this primarily means is that the magnitude of the line voltage is root 3 times the magnitude of the phase voltage, and the line voltage leads the phase voltage by 30 degrees. Therefore, we say that VL is equal to root 3 times VP. So this is the relationship between the line and phase voltages for a star configuration. Now let's move on to the current relation. So for the current relation, let's consider that we have ZP to be the impedance per phase, and then we have IA, IB, and then IC to be the line currents. Now from KVL, we have IA equals VAN divided by ZP, and then we have VAN to be V polar 0, so divided by ZP, and then V polar 0 is the same as V, so we have V divided by ZP. Now let's call this equation 1. Now to IB, we also have VBN divided by ZP. VBN is equal to V polar negative 120 divided by ZP. Now from equation 1, you realize that IA is equal to V over ZP. Therefore, we can substitute I in place of V over ZP, so that we have IB equals IA polar negative 120. Let's call this equation 2. Now also for IC, we have IC equals VCN divided by ZP, and that is equal to V polar plus 120 divided by ZP. Now V over ZP is equal to IA, so that becomes IA polar plus 120. Now what this primarily means is that the line current IL is equal to the phase current IP in a star configuration, and both the line current and the phase current have the same phase. Notice also that adding up the 3 line currents, that is IA plus IB plus IC, is equal to 0, so that the current in the neutral is equal to negative of the sum of these values. So negative of 0 is equal to 0, and thus the voltage across the neutral is equal to Zn times the current in the neutral, and because the current in the neutral is 0, we have the voltage across the neutral also to be 0. Thus, removing the neutral wire does not have any significant effect on the 3-phase system. Now let's move on to the relationship between VL, VP as well as IL, IP for a delta configuration. So considering a balanced delta-delta system, we have 3 terminals A, B, C, And notice that in a delta configuration, there is no neutral point. The windings are connected end to end. So we have this to be terminal A, terminal B, and then terminal C. And then we have the phase voltage, VAB, VCA, and then VBC. And then we have the lines L1, L2, and then L3. Now for the relationship between the phase and line currents and voltage for a delta connection, we are basically going to interchange the relationship we had for the star configuration. So for a balanced delta configuration, the line voltage is said to be equal to the phase voltage, and the line current is equal to √3 times the phase current. So in summary, for a star configuration, the line voltage is equal to √3 times the phase voltage, and the line current is equal to the phase current. For a delta configuration, the line voltage is said to be equal to the phase voltage, and the line current is equal to √3 times the phase current. Now let's move on to the power relation for the two modes of connections. The total power in a three-phase circuit is the sum of the power in all the three phases, so that in a balanced system, be it delta or star connected, the total apparent power, which is given as S, is equal to √3 times VL times IL. Now let's call this equation 1. Now from this equation, we have the active power given as P equals S cos phi. And then we have S to be √3 times VL times IL times cos phi. Let's call this equation 2. And the reactive power is given as S sin phi, and that's also equal to √3 times VL times IL times sine of angle phi. Notice that cos phi is equal to the power factor. Now let's move on as we solve a couple of examples. So let's take our first example. 3 identical resistors are connected in star across a 3-phase 415 volt supply. If each resistor has a resistance of 100 ohms, calculate A, the voltage across each resistor, B, the current in each resistor, and then C, the total power supplied to the load. Now let's try this question together. So considering this question, we have 3 identical resistors connected in star, which means that those 3 resistors have the same value of resistance, and hence we have a balanced load system. We are being told that the supply voltage, that is the line voltage, is 415 volts, and then we have a star configuration. So we have VL to be 415 volts, and then we have the configuration to be star, and then we have the resistance in each phase to be 100 ohms. So we can say that ZP is equal to 100 ohms, and then we know that the impedance is solely due to the resistor. So A, we are asked to find the voltage across each resistor. Now the voltage across each resistor means that we are asked to find the voltage in each phase, or the voltage per phase. Now considering a star configuration, we know that the line voltage is equal to root 3 times the phase voltage. Therefore, we have the phase voltage to be equal to VL over root 3. We have the value for VL to be 415, and then divided by root 3. And then when you divide 415 by root 3, you have 239.6 volts. So this is the voltage across each resistor. B. We are going to find the current in each resistor. So the current in each resistor represents the current in each phase. So from Ohm's law, we know that the voltage per phase is equal to the current per phase times the impedance per phase. Now we have the impedance per phase to be 100 ohms, and then we have the voltage per phase to be 239.6 volts. Therefore, we can find the value of the current in each phase, and that is equal to Vp divided by Zp. We have the voltage per phase to be 239.6 divided by impedance per phase, that is 100 ohms, and then we are going to have 2.396 amperes. C. We are going to find the total power supplied to the load. Now, considering this circuit, you realize that the impedance in this circuit is solely due to the resistor. Therefore, the total power supplied to the load is the active power. Now, we said that the active power P is given as root 3 times VL times IL times cosine of angle phi. Now, because the impedance of the circuit is due to only the resistor, it means that the power factor is unity, and that is equal to 1. Therefore, to find the value of the total power supplied to the load, that is given as root 3 times VL, which is given in the question to be 415, times IL. The line current is equal to the phase current, that is IL is equal to IP. So in place of IL, we have 2.396 and then times 1. So when you multiply all these values, you are going to get 1722 watts, and that can be expressed as 1.722 kilowatts. So that is the total power supplied to the load. Now let's move on to our second example. 3 identical impedances are connected in delta across a 3-phase 415 volts supply. If the line current is 10 amperes, calculate A, the current in each impedance, and then B, the value of each impedance. So for this question, we have a delta-delta balanced system, and thus we have the line voltage to be 415 volts. We have the line current giving us 10 amperes, and then we have the configuration to be delta. Now we are asked to find A, the current in each impedance. Now, because this is a delta network, we know that the line current is giving us root 3 times the phase current, and the current in each impedance is basically the phase current. So let's try to find the phase current, and that is giving us IL divided by root 3. So we have IL given in the question to be 10 amperes divided by root 3, and that is equal to 5.773 amperes. So this is the value of the current in each impedance. B, we are asked to find the value of each impedance. Now, because the system is a balanced system, the voltage per phase is equal to the current per phase times the impedance per phase. Now, from this relation, we can find the impedance per phase. So the impedance in each phase, or the value of each impedance, is giving us the voltage per phase divided by the current per phase. Now we have the voltage per phase to be equal to, now because we have a delta network, in a delta network, the line voltage is equal to the phase voltage, and that is equal to 415 volts. Therefore, we have Vp to be 415 divided by Ip, that is 5.773. So 415 divided by 5.773 is equal to 71.87. So we have the impedance in each phase, or better still, the value of each impedance to be 71.87 ohms. Now let's move on to the last example. A 3-phase 450 volt system supplies a balanced delta connected load at 12 kilowatts at 0.8 power factor lagging. Calculate A, the phase currents, B, the line currents, and then C, the effective impedance per phase. So from this question, we have the line voltage to be 450 volts. The configuration is a delta configuration. We have the active power giving us 12 kilowatts. We have the power factor to be 0.8 lagging. And then we are asked to find A, the phase currents, and then B, the line currents, and then C, the effective impedance per phase. Now we know that the active power P, or the total active power P, is giving us root 3 times VL times IL times cosine of angle phi. We have the value of P, we have the value of VL, we have the value of cos of angle phi, which is the power factor. We can find the value of the line current. So the line current IL is equal to P divided by root 3 times VL times cos of angle phi, and then that is equal to, we have the value of P to be 12,000, that is 12 kilowatts, divided by root 3 times VL, which is giving us 450, and then times cos of angle phi, which is giving us the power factor 0.8. So dividing 12,000 by root 3 times 450 times 0.8, you are going to get 19.245, and that is the value of the line current. Now we are asked to find the phase current, that is for A, and then we know that for a delta connection or for a delta configuration, the line current is equal to root 3 times the phase current. Therefore, the phase current is equal to the line current divided by root 3, and then we have IL to be 19.245 divided by root 3, and that is equal to 11.11. amperes. So this is the value of the phase current. Now the value of the line current, we had that in our calculation to be 19.245 amperes. So we are done with that. Now let's move on to C, that is the effective impedance per phase. Now the impedance per phase is giving us the voltage per phase divided by the current per phase. Now we have the voltage per phase to be equal to, now because we are considering a delta connection, the line voltage is equal to the phase voltage. So that is equal to 450. So we have 450 divided by IP, which we had to be 11.11. And so dividing 450 by 11.11, you have 40.5. Now for the phase angle, we have the power factor giving us 0.8 lagging, and that is equal to cosine of angle phi. Therefore, to find angle phi, that is equal to cos inverse of 0.8, and that is giving us 36.9. So this is the phase angle. So back to the impedance. Now this value, which is 40.5 ohms, is said to be the polar impedance. Therefore we have ZP to be equal to 40.5 polar. Now the phase angle 36.9. Hence the effective impedance per phase. So that's it for today's video. Thanks for watching, and see you in my next video. Bye bye.